Hello my friends and welcome back to the You Can Do TV channel. In this video we'll learn about process of manufacturing and assembling marine engine, and in the next sections of the video, we will discover other amazing production processes.
The Caterpillar marine engine manufacturing process at the Lafayette, Indiana facility, based on these steps: engine block test and machining. The engine block is first tested for any defects or imperfections. Then, the block is machined to the required specifications using advanced CNC machines and equipment. Connecting rods are precisely machined using specialized equipment to ensure that the bore diameter, roundness, and taper meet the required specifications. Plasma valve machining is a high-precision process used to create complex valve shapes and features in engine components. This process uses a combination of plasma arc and CNC machining to create intricate details and features in valves that would be difficult to achieve using traditional machining processes. Cylinder heads are precisely machined to ensure that they meet the required specifications for combustion chamber shape, valve seats, and port geometry. This process includes milling, drilling, and grinding to ensure that each cylinder head is machined to the required tolerances. Crankshaft test process. The crankshaft is also tested for any defects or imperfections. Robotic rod machining. The connecting rods are machined using advanced robotic machines to ensure precision and accuracy. The crankshaft is carefully positioned and installed into the engine block. Specialized equipment, such as an alignment gauge, is used to ensure that the crankshaft is installed in the correct position and alignment. Piston and rod installation. The pistons and connecting rods are then installed into the engine block, and the entire assembly is carefully inspected to ensure that everything is in place and functioning properly. Smart tooling. Advanced smart tooling is used throughout the manufacturing process to ensure precision and accuracy. (3,600) crankshaft installation. The 3,600 crankshaft is installed into the engine block, and the entire assembly is carefully inspected to ensure that everything is in place and functioning properly. On-site testing of every engine. Each engine is then tested on-site to ensure that it meets the required performance and quality standards. This includes a range of tests, such as functional, durability, and emissions testing. Robotic paint process. The engine is painted using advanced robotic equipment to ensure a uniform and high-quality finish. Final inspection. The engine undergoes a final inspection to ensure that it meets all the required quality standards and specifications. Any defects or issues are addressed before the engine is shipped out. The power generation industry has a significant need for the production and replacement of gears, shafts, and gearboxes. Coal-fired power plants, in particular, have been built in large numbers within a 350-mile radius of HMC, heavy machinery components, a reputation for providing superior service. This company is known for its advanced technology manufacturing and service capabilities, along with its rapid response to breakdown emergencies. HMC specializes in the production and replacement of gears, shafts, and gearboxes for the power generation industry. The production process involves various steps such as turning, welding, stress relieving, and magnetic particle inspection. The company's production facilities are state-of-the-art, equipped with modern onboard inspection and software technology that can substantiate gear quality to 240 inches in diameter. HMC uses 21st century advanced technology, forged and cast steels that offer increased hardness and strength and improved wear resistance while remaining forgiving even when operating temperatures drop below -40 degrees Fahrenheit. HMC's production process for gears involves turning the web plate to size, getting the ring ready for welding, welding the gear, stress relieving the gear, magnetic particle inspection, and finishing the split line and bolt holes. For shafts, the production process involves cutting, drilling, chamfering, and heat treatment. Gearbox production involves a series of steps such as disassembly, inspection, cleaning, reassembly, testing, and painting. The power generation industry depends on high-quality, long-lasting ball mill gears. These gears can be produced by companies that meet specific qualifications and standards, such as AGMA Quality 12. The production of these gears requires advanced technology and expertise in material selection, design, and quality assurance. In recent years, the cost of materials for large gears and other machine components has increased significantly, making replacement parts more expensive. However, there are companies that offer cost-saving repair solutions that carry new warranties. Refurbished gears are also available, which can provide cost savings while still offering a new gear warranty. Companies that produce and replace gears, shafts, and gearboxes play a vital role in the power generation industry. They must meet strict qualifications and standards to produce high-quality, long-lasting parts. The use of advanced technology, material selection, design, and quality assurance is essential to the production process. Additionally, these companies must provide rapid response times and offer cost-saving repair solutions to support the industry's needs. At HMC, the production process for gears involves several steps. First, the web plate is turned to size. Then the ring is prepared for welding. After the gear is welded, it undergoes stress relieving to ensure its strength and durability. Magnetic particle inspection is carried out to check for any cracks or defects in the gear. Finally, the split line and bolt holes are finished to complete the gear. The production process for shafts at HMC involves cutting, drilling, chamfering, and heat treatment. Cutting is done to ensure that the shaft is the right size, while drilling and chamfering are carried out to create holes and angles in the shaft. Heat treatment is used to strengthen the shaft and make it more resistant to wear and tear.
The production process of a Torino alloy rim wire wheel begins with the preparation of the rim, starting with a 5-meter length of thick-walled 5000 series aluminum tube. This tube is cut to the appropriate length using a bandsaw. The cutting leaves rough edges, necessitating further refinement. The tube is then turned on a lathe to square the edges and achieve a smooth finish. This step is critical, as any imperfections could lead to cracks or splitting during subsequent operations. Once the edges are satisfactorily finished, the tube is transferred to a 200-ton press. Here, it undergoes its initial shaping, guided by a custom-designed plug tailored to the desired rim diameter. Different tube sizes and plugs are utilized for each rim diameter, ensuring precision. The tube is gripped by clamshell tooling, also purpose-built in-house, preparing it for the spinning operation. Approximately 30 clamshell tools, one for each rim size, are maintained for this purpose. After the initial press, the tube is checked for fit and shape by measuring the distance from the rim to the edge of the tool. If the measurements align with specifications, the opposite side of the tube is pressed, securing a snug fit. Next, the tube is transported to Sapphire Spinning Letate in Harlow, where it is mounted onto a computer-controlled spinning machine. With the application of heat and lubrication, the tube is gradually shaped through multiple passes of a spinning roller. This process continues until the tube conforms precisely to the tooling's contour on the tire side of the rim. Once complete, the tooling is unclamped, and the partially formed rim is returned to the machine shop for further processing. Upon return, the raw spun rim enters the fine-tuning stage. It is placed into a large rim lathe, where the inside of the rim is shaped further, and the thickness is adjusted according to the wheel's design and intended application. This step allows for customization, as thickness can vary to meet specific performance or aesthetic requirements. The lathe work ensures the rim's structural integrity and prepares it for the next phase. For wheels destined to have a polished finish, the rim proceeds to the polishing stage. This process occurs in two distinct steps to achieve a mirror-like shine. Initially, the rim is sanded using a range of grits, starting with a coarse grade and progressing to finer ones. This smooths the metal surface, eliminating imperfections. Following sanding, the polishing begins, employing a series of grit mops in a similar coarse-to-fine progression. As the finer grits are applied, the rim's reflective quality emerges, highlighting the craftsmanship involved. Unlike automated processes, this stage relies heavily on skilled hands, with each rim receiving individual attention to ensure perfection. The rim then moves to the marking and preparation phase. The wheel is marked according to its specific design, such as the number and arrangement of spoke rows, ranging from single to triple rows, as seen in a 72-spoke configuration, with 3 distinct rows. Dimples are pressed into the rim at these marked points, shaped to accommodate spoke nipples securely and accurately. Concurrently, the wheel center, typically made from polished stainless steel to prevent rust, is drilled to match the spoke pattern. The rim itself is drilled at precise angles for the bottom, middle, and top rows of spokes. Test holes are drilled initially to verify alignment before completing the full set. A custom attachment ensures the holes align with the dimple radii, preventing spoke misalignment. After drilling, the rough edges are deburred, using a specialized drill bit, followed by hand deburring for a flawless finish. Finally, the wheel assembly begins. Spokes, available in pre-polished stainless or carbon steel, are measured, bent to the correct angle, and cut to length based on the wheel's offset. These are threaded using a thread rolling machine, which enhances thread strength compared to traditional die-cutting methods. Assembly proceeds row by row, starting with the middle and working outward, with spokes inserted according to the designated pattern. Once all spokes are in place, they are tensioned while the offset is monitored. The wheel is then trued on a custom jig, with each spoke carefully adjusted to ensure the rim runs perfectly straight. Within a tolerance of less than 1 millimeter, though typically under 0.5 millimeters. A dial gauge confirms trueness, and upon completion, the builder stamps the job number and their initial inside the rim, signaling approval. The finished wheel is packaged using specially designed materials to protect the delicate alloy rim during shipping, a precaution refined after early transport mishaps.
Steel coil production begins with the extraction of iron ore, a fundamental raw material, sourced globally from regions like Russia, South America, Africa, and Australia. The ore, arriving as lumps, fines, or pellets, small baked balls of iron concentrate, is transported by ship and rail to facilities like Salzgitter AG. At the plant, towering blast furnaces, some over 50 meters tall, process up to 14,000 tons of pig iron daily. Inside, layers of coke, ore, and limestone descend, heated by process gas generated from air blasted at 1,500 degrees Celsius. This reduces and melts the ore into molten iron and slag, tapped every 2 hours at 1,450 degrees Celsius. The pig iron is then transferred via torpedo ladles to a steelworks, where it's poured into converters alongside scrap. Using the LD process, pure oxygen refines the melt, removing impurities and reaching temperatures around 1,700 degrees Celsius in about 40 minutes, yielding raw steel. Alloying elements like manganese or chromium are added to tailor the steel's properties. The molten steel is cast into slabs, rolled into coils in a hot rolling mill at 1,250 degrees Celsius, and cooled. These coils, often up to 2,000 meters long, serve industries worldwide, from construction to automotive. Smooth metal sheets are fed into the rolling mill, where they pass through a series of rolling stands. Each stand incrementally bends the metal, gradually forming the desired profile. For specific products like metal tiles, transverse steps are stamped at set intervals. The rolling mill for shaping smooth metal sheets is manufactured starting with cutting metal blanks from rolled stock. These blanks are machined into components, such as shafts and profiling rollers, using high-precision centers. Frames are welded and painted, then assembled with uncoilers and guillotine shears. Rollers are mounted on shafts, aligned and synchronized, ensuring the mill shapes the metal efficiently and accurately. The Datron high-speed milling machine efficiently produces a high-end electronics housing by leveraging its advanced capabilities. The process begins with a milling strategy that utilizes the full 26 mm cutting length of tool No. 2, employing a Z-axis infeed to maximize material removal. This is followed by dynamic machining of a pocket with a 1 mm transverse feed, optimizing speed and reducing tool wear compared to traditional methods. The machine's high-speed precision spindle, capable of reaching up to 60,000 RPM, ensures rapid cutting while maintaining accuracy. Its large 40 inches by 33 inches work area accommodates the housing, despite the machine's compact 69 inches by 69 inches footprint. The rigid, low-vibration design enhances surface quality, critical for intricate electronics components. The workflow is streamlined as the machine sets up jobs quickly, often in minutes, minimizing downtime. For this housing, the machine dynamically adapts to complex geometries, reducing cycle time by over 50% compared to conventional vertical machining centers. Secondary operations are minimized or eliminated due to the precision and versatility of the spindle and tooling. Operating with low costs, the machine handles aluminum and non-ferrous metals effectively, making it ideal for such detailed parts. This combination of speed, precision, and efficiency delivers a high-quality electronics housing in a short production window. The Kohler cut-to-length line with a special saw operates by processing strip material through a series of precise, automated steps. Strip material is first drawn from a coiler, where it is unwound and fed into the system. A leveling mechanism then straightens the material, ensuring it is flat and free of distortions. Once leveled, the material advances to the cutting stage, where a specialized saw trims it to the exact length specified, achieving millimeter accuracy. This cutting process is tailored to maintain the material's integrity, avoiding damage or imperfections. After cutting, downstream stacking lines handle the finished pieces, employing scratch-free destacking techniques to preserve surface quality. Options such as magnetic strip stackers, vacuum belt stackers, or brush roller stackers manage the stacking, while cropping, cut to length, or swiveling shears provide flexibility in cutting configurations. Centralized control systems oversee the operation, ensuring precision and efficiency throughout the process. A complex turned part with threading produced by a CNC machine reflects key manufacturing metrics. Consider a component like a precision spindle, commonly used in automotive or aerospace sectors. This part might have a 50 mm length, a 20 mm major diameter, and an M12 by 1.75 thread spanning 15 mm, with a 10 mm shoulder and a 5 mm deep relief groove, machined to a tolerance of plus or minus 0.01 mm, a standard reflecting the 2023 industry average for high-precision components. CNC lathes, which account for 28% of the $12.4 billion global machine tool market, per 2024 industry reports, typically start with 25 mm diameter stock, such as 316 stainless steel, valued for its 15% share in precision machining materials. Rough turning reduces the diameter to 21 mm at 2000 RPM and 0.3 mm rev, aligning with the 85% utilization rate of carbide tools industry-wide. Finish turning then achieves the 20 mm diameter at 2500 RPM and 0.15 mm rev, meeting the 0.8 micrometers raw surface finish demanded by 90% of Tier 1 automotive suppliers. Threading, a process applied to 40% of turned parts per 2023 production data, uses a 60-degree single-point tool at 800 RPM. The G76 cycle executes passes with depths decreasing from 0.5 mm to 0.1 mm, producing the 1.75 mm pitch and 1.082 mm thread depth, consistent with ISO standards adopted by 95% of manufacturers. The relief groove, cut at 1500 RPM, supports the 30% increase in multi-feature components noted in 2024 industry trends. Inspection via CMM, used in 65% of precision shops, confirms the 11.188 mm pitch diameter and concentricity, while production time averages 12 minutes to 10% below the industry mean of 13.3 minutes for similar parts. This reflects CNC's role in driving a 3.5% annual growth in machining efficiency, per 2025 forecasts. Forging a railway component, specifically a locomotive chassis part weighing around 100 kilograms, begins with pre-forging using a 1959 pneumatic hammer delivering 900 kilojoules to roughly distribute the steel material. Next, an electro-hydraulic drop forge hammer from 2003, with 1,250 kilojoules capacity, shapes the part using a die, though the component exceeds the hammer's ideal size. The process requires 3 heating cycles, initially to 1,200 degrees Celsius, followed by 2 reheats in a gas-fired forge furnace, demanding over 100 strikes for final forging. After each forging stage, a 1982 400-ton press trims excess material. A manipulator handles the 300 kilograms part, while 3 skilled workers collaborate seamlessly, making it a fascinating display of teamwork and expertise.
Crankshaft machining is a crucial process in the production of high-performance engines, and it requires precision and accuracy. The Nakamura WT300 is a versatile machine that is well suited for this type of work. This machine has the capability to perform turning, milling, and drilling operations on a variety of materials, including hardened steel. In this part, we will discuss the process of crankshaft machining on a Nakamura WT300. The first step in the crankshaft machining process is to set up the machine. This involves installing the necessary cutting tools, setting the workpiece on the chuck, and adjusting the machine's parameters to ensure the proper speed and feed rate. The Nakamura WT300 has a built-in tool setter that helps to automate this process, which helps to reduce setup time and improve accuracy. Once the machine is set up, the next step is to begin the turning process. The turning operation involves removing material from the workpiece to achieve the desired shape and dimensions. The Nakamura WT300 has a powerful spindle that is capable of high-speed turning, which helps to reduce cycle times and improve productivity. The machine also has a high-precision servo-driven turret that can hold multiple cutting tools, which allows for rapid tool changes and greater flexibility in the machining process. After the turning process is complete, the next step is to perform milling operations. Milling involves using a cutting tool to remove material from the workpiece in a specific pattern or shape. The Nakamura WT300 has a live tooling system that allows for milling operations to be performed directly on the machine, without the need for a separate milling machine. This helps to reduce setup time and improve accuracy, as the workpiece does not need to be moved between machines. Finally, after the milling process is complete, the last step is to perform any necessary drilling operations. This involves creating holes in the workpiece to accommodate bearings or other components. The Nakamura WT300 has a high-speed spindle that can perform drilling operations quickly and accurately, which helps to reduce cycle times and improve productivity. Piston machining is a process that involves the creation of pistons, which are essential components in internal combustion engines. Piston machining involves the use of various machines and tools to create the precise shapes and sizes required for different engine types. At Race Tech Pistons, a high-performance piston manufacturer located in Huntington Beach, California, the machining process involves 7 main operations. The first operation at Race Tech Pistons is called the twin spindle, which involves loading a specific forging into the CNC machine. The CNC machine is then programmed to cut and shape the forging to create the required design for the piston. The second operation is called the lathe, where the ring grooves and gas distribution grooves are cut into the piston. The third operation at Race Tech Pistons is the pin bore machine, which is responsible for drilling the pinhole for the piston. This machine also creates lateral gas ports, split oil drain backs, and double pin oilers. The fourth operation is the side relief machine, where the pistons are trimmed to optimize weight and pin length. The skirts are also internally milled to achieve the correct thickness for the specific engine application. The fifth operation is the 5-axis dome and profile machine, which is capable of cutting dome profiles, dish profiles, valve reliefs, and vertical gas ports. The machine can turn in 5 different directions and can handle up to 9 pistons at a time, making it highly efficient.
Take a little bit of material off.
The sixth operation is the tank machine, which is used to cut off the registers used in the previous operations. After this, the piston is trimmed to the final skirt size.
And inspect it from this point on.
The last operation is the cam turn, which is where the piston receives its final bore diameter and gram weight. Each operation in the piston machining process is critical to ensuring that the piston is precisely manufactured to meet the customer's specific requirements. At Race Tech Pistons, the finished product is deburred and inspected to ensure that the weights and sizes match the customer's order.
Fabrication involves constructing large-scale metal structures and components, often for industrial applications. The process begins with raw materials, such as steel beams, channels, and plates, which are cut, shaped, and assembled according to precise blueprints. Advanced equipment, like high-capacity bridge cranes, some with 30-ton or 40-ton lifting capabilities, facilitates handling oversized pieces. Welding, including seam welding with tools like bug-o welders, joins components efficiently, minimizing seams by utilizing large sheet sizes. Facilities boast expansive floor space and overhead crane systems, enabling smooth movement and assembly. Additional steps, such as rolling plates, saw cutting structural members, and painting in spacious booths, ensure finished products meet customer specifications for durability and precision. The Gorillacher Combi T operates efficiently to produce standing lock seam elbows and reducers. Two separate workstations, a flanging station and a seam closing station, enable high flexibility, allowing continuous operation without time-consuming conversions. Sheet metal is first processed at the flanging station, where edges are shaped, then transferred to the seam closing station to form the standing lock seam. This design reduces welding to a single longitudinal seam while enhancing rigidity. With a capacity for material up to 1.5 mm thick, the machine delivers constant quality at high production speeds. Hardened steel rotating tools ensure durability, requiring virtually no maintenance or lubrication, resulting in high-quality seams. The process of operating a flanging machine for sheets up to 3.75 mm thick begins with preparing the workpiece. The center of the piece is drilled, creating a hole with a diameter of 16 mm. Next, the fixing screw at the center is removed, and the workpiece is secured in place using the screw. The distance is then adjusted according to the desired flange height. In this example, a 10 mm setting is used to reach the machine's limit. Once the setup is complete, the headstock motor is activated, engaging the pulley system. The spindle is tightened gradually, with a ratio of half a spindle turn for each full rotation of the sheet. As the pulleys press against each other, they form a 45-degree angle. At this point, the lifting motor is engaged, raising the headstock to achieve the desired inclination. This systematic approach ensures precise flanging, shaping the sheet effectively while maintaining control over the angle and height of the flange. The process concludes when the headstock reaches the specified position, completing the transformation of the sheet. The roll threading machine creates threads on a workpiece by cold forming metal using hardened steel dies. The process involves rotating the workpiece between 2 or 3 cylindrical dies with thread profiles. As the dies apply pressure, the metal is displaced and reshaped into the desired thread form without cutting or removing material. This method enhances thread strength due to work hardening. The machine's precision adjustments control thread size, depth, and pitch, making it efficient for producing uniform, high-quality threads in mass production. Kimla CNC machines, produced by a Polish company based in Częstochowa, exemplify a manufacturing process centered on precision and efficiency, leveraging advanced fiber laser technology. The process begins with designers creating technical drawings tailored to specific factory requirements. These designs are then distributed to production departments for execution. Heavy-walled steel profiles, sourced directly from ironworks, form the machine's main body. A plasma profiling machine cuts these profiles to precise lengths and shapes, adding service and structural openings. After cutting, the pieces undergo shot blasting to ensure smooth, clean surfaces before heading to fabrication. In the fabrication department, profiles are fixed onto a welding panel, welded, and cleaned at the joints. The resulting frame is then machined using a multi-axis milling machine, enabling the production of large, highly accurate components down to micromillimeter precision in a single operation. Post-machining, the frame is painted with protective and aesthetic coatings. Meanwhile, other components, often made from lightweight aluminum alloys to optimize the machine's dynamic performance, are cut using water jets or Kimla's own fiber lasers, bent and powder-coated for durability. Assembly occurs in a systematic, automated line, where linear motors, control cabinets, and custom software are integrated. After rigorous testing, the completed machines are ready for delivery. The production of 120 mm steel balls using a skew rolling mill machine involves a precise and efficient process. Steel rods, typically made from alloys suited for grinding applications, are heated to a high temperature in a furnace, reaching a malleable state. These heated rods are then fed into the skew rolling mill, such as the D120 model operational in Armenia, where 2 specially designed rollers rotate at an angle. The rollers shape the material into spherical forms through continuous rotation and pressure, ensuring uniformity in size and structure. As the steel balls emerge, they undergo rapid cooling or quenching to enhance hardness and durability. Afterward, a tempering process relieves internal stresses, improving toughness. The finished 120mm steel balls are polished and inspected for quality, ensuring they meet standards for use in industries like mining, cement, and thermal power, where grinding efficiency is critical. The production process of hydraulic cylinders in Rissa, Norway begins with in-house design using sophisticated simulation tools like Simulation X to analyze and virtually test complex mechatronic systems, ensuring functionality. Manufacturing utilizes the Mosaic Integrex, a multitasking machine combining CNC turning and machining, enhancing precision. Submerged arc welding, executed by certified DNV operators, ensures high-quality joints for large tubes. Cylinders, ranging from 20 to 2,000 millimeters in piston diameter and stroke lengths up to 20 meters, undergo pressure testing, function testing, and cleanliness control to meet offshore standards and customer specifications. The facility integrates renewable energy via heat pumps, retrieving stored energy from the sea, optimizing efficiency and sustainability. A pneumatic power hammer, designed as a riser casting headbreaker, operates by using compressed air to drive a piston. This piston powers a hammerhead that delivers forceful impacts to remove casting heads or risers from castings. The same mechanism allows it to break foundry shells efficiently, enhancing post-casting cleanup in foundry operations. The FS8 grinder processes springs between 3/4 and 4 inches long, delivering high-precision results. Springs are placed on a central plate, where a single grind wheel, spinning opposite the plate, engages them for a square grind. Conversely, Bennett grinders handle springs from 4 inches to 24 inches long. Loaded into turret fixtures, springs are ground squarely by 2 large wheels rotating against the turret's direction. The production process here involves manufacturing vessel bottoms using advanced equipment. Elliptical, flat, toruspherical, and conical bottoms are produced from steels like ST3, IC304, and IC321, with ultrasonic weld inspection and heat treatment. Hot stamping ensures compliance with GOST 6533 standards. These components suit gas firefighting systems, pressure vessels, and pipeline networks.
Crankshafts are essential components in internal combustion engines used to convert the reciprocating motion of the pistons into rotary motion. The manufacturing process of crankshafts is crucial for ensuring their durability, strength, and performance. In this video, we will discuss the forged crankshaft manufacturing process using drop forging. Drop forging is a popular method for manufacturing high-strength, high-durability components. The process involves heating a metal billet to a high temperature and then using a hammer or press to deform the metal into the desired shape. Forging makes the metal stronger and more durable than other manufacturing processes like casting or machining. The forged crankshaft manufacturing process using drop forging involves the following steps. Billet preparation. The first step is to prepare the billet, which is a piece of metal that will be used to create the crankshaft. The billet is typically made from steel, which is a strong and durable material. The billet is heated to a high temperature, which makes it more malleable and easier to shape. Forging. The heated billet is then placed in the forging machine, and the hammer or press is used to apply pressure to the metal, shaping it into the desired form. The crankshaft is formed by using dies that are designed to create the specific shape of the crankshaft. Heat treatment. After the forging process is complete, the crankshaft is heat treated to improve its strength and durability. The heat treatment process involves heating the crankshaft to a high temperature and then cooling it rapidly. This process helps to create a tightly packed grain structure that enhances the strength and durability of the material. Machining. The final step is to machine the crankshaft to the desired dimensions and surface finish. This process involves using a lathe or milling machine to remove any excess material and to create the required shape and surface finish.
Industrial bearing production involves a sophisticated and highly controlled process to manufacture tens of thousands of bearing types, catering to diverse industrial applications such as electric vehicles, robotics, aviation, and construction machinery. The process begins with the selection of premium raw materials, emphasizing steel purity. Stringent standards regulate elements like oxygen, titanium, sulfur, and phosphorus, with oxygen levels kept below 10 parts per million to enhance steel purity and extend bearing lifespan. Depending on the bearing size and performance needs, either turned or forged rings are utilized. 5 dedicated rolled ring production lines ensure precise control over initial and final forging temperatures, improving ring compactness through forging. Heat treatment follows, employing 3 advanced lines with a protective atmosphere salt bath process. This method stabilizes the treatment, enhancing material rigidity, compactness, and dimensional stability to support high-load performance. Each batch undergoes online inspections for hardness and metallography, with customizable heat treatment options available to meet specific requirements. The grinding phase relies on over 80 third-generation automatic grinding lines developed through years of research. These lines handle large-scale production, performing automated grinding and real-time dimensional inspections to ensure consistent quality and efficiency. Assembly occurs across 33 automated lines, integrating processes like parts feeding, demagnetization, cleaning, ring and ball matching, cage installation, grease filling, shield pressing, anti-rusting, and laser marking. Equipped with online measurement systems for ring dimensions, rolling element sorting, vibration, and clearance checks, these lines feature error prevention devices to maintain quality uniformity. For smaller batches or varied specifications, numerous independent grinding machines and flexible assembly lines provide adaptability. Quality control underpins the entire process, adhering to a rigorous management system. Inspections occur at every stage, from raw material intake to production processes and final product checks, achieving a market defect rate below 10 parts per million.
China is the world's largest producer of hydraulic cylinders, with an annual output exceeding 30 million units. The industry is driven by over 2,000 manufacturers, mainly concentrated in Jiangsu, Zhejiang, and Shandong provinces. Leading companies contribute significantly to both domestic and export markets. The market size reached approximately $8 billion in 2023, with exports accounting for over 25% of total production, mainly to Europe and North America. China produces a wide range of cylinders, including welded, tie rod, and telescopic types, catering to industries like construction, agriculture, and automation. Advanced manufacturing techniques such as robotic welding, CNC machining, and precision honing enhance quality and efficiency, solidifying China's dominance in the global hydraulic cylinder market. The Francis turbine machining industry is essential for hydroelectric power generation, as it ensures the precision manufacturing of critical components such as runner blades, guide vanes, and casings. Given the complex 3D geometry of these parts, high-precision machining is required to optimize efficiency and durability. Advanced 5-axis CNC milling machines and robotic welding systems are commonly used to achieve the necessary accuracy and surface finish. The runner diameter in Francis turbines typically ranges from 0.35 meters to 10 meters, depending on the power capacity of the hydroelectric plant. Runner blades require a machining tolerance of plus or minus 0.02 millimeters, achieved through high-speed milling, electrical discharge machining, and laser measurement systems. To withstand high water pressure and cavitation, stainless steel alloys are used. Large-scale Francis turbines, often exceeding 100 megawatt capacity, require CNC gantry milling machines capable of handling workpieces over 50 tons. Machining cycle times vary, with runner production taking 6 to 12 months, including rough machining, stress relief treatments, and final precision finishing. The industry continues to advance with robotic automation and AI-driven quality control, ensuring high-performance turbines for sustainable energy production.